already seen antiderivatives for sine and for cosine.
So what's an antiderivative for, say, cosine 3x? Right, I'm looking for some function that differentiates to cosine 3x.
Well, there's basically one trick that we've been using throughout all of these antidifferentiation problems. It's guessing.
Sine differentiates to cosine, so maybe sine of 3x is a good guess. But if I differentiate sine of 3x using the chain rule, I get the derivative of the outside function. That's looking good. At the inside function, that's looking good too. But times the derivative of the inside function, which is 3. So that's no good. But I can fix that pretty easily, right? If I just include a 1/3 here, that rigs up everything perfectly, right? Because then the 1/3 here and the 3 cancel, and I'm left with cosine of 3x. So I can summarize this by saying that an antiderivative for cosine 3x is 1/3 sine 3x, and then to get any other antiderivative, I just add some locally constant function c.
Well, that worked out. Let's try to do a slightly harder example.
Let's try to antidifferentiate, say, sine of 2x plus 1. Right? I'm looking for some function which differentiates to sine 2x plus 1.
I might guess that the answer will involve cosine.
Well, I know that cosine differentiates to minus sine, so my first guess might be cosine of 2x plus 1, because if I differentiate this, I get minus sine of the inside function times the derivative of the inside function. So this is not exactly this, so I haven't quite found an antiderivative, but it'll be easy to patch that up, right? If I instead look at a slightly different function, if I include a factor of minus 1/2 in front of cosine of 2x plus 1, then the derivative will be minus 1/2 times the derivative of cosine 2x plus 1, which is minus sine 2x plus 1 times 2. And now the good news is that the minus 1/2 and this minus sign and this 2 cancel, and what I'm left with then is just sine of 2x plus 1, which means I've found an antiderivative, right? An antiderivative for sine of 2x plus 1 is, according to this argument, negative 1/2 cosine 2x plus 1 plus some constant c.
I can see a bit of a general principle here.
Well, here's our setup. I've got m and b, just a couple constants. And what I want to do is antidifferentiate a function evaluated at mx plus b. All right, this is the general framework that's general enough to encompass the examples we've done thus far, right? F could be, say, sine or cosine. In our first example, we looked at cosine of 3x, so m was 3 and b was 0. In our second example, we looked at sine of 2x plus 1, so m was 2 and b was 1 and f was sine. But this is sort of a general example that encompasses some of the specific examples we've already taken a look at. Let's suppose that you already have an antiderivative for little f. Yeah, let's suppose that I know how to antidifferentiate just f, and let's call that big F. Right? So the derivative of big F is little f.
Now, how do I deal with the mx plus b part?
Well, basically trying to guess, right? I'm trying to find some function that differentiates to this, and I've got a function that differentiates to just f. So let's see what happens if I differentiate big F of mx plus b by using the chain rule. Well, the derivative of big F is little f, evaluated at the inside, times the derivative of the inside, which is just m. Now I can fix this. If I include a factor of 1 over m here, then I get a factor of 1 over m here, and that's great because then this 1 over m and this m cancel. So here I've got a function whose derivative is f of mx plus b. In other words, the antiderivative of f of mx plus b is this, right? It's big F of mx plus b divided by m plus c.
Instead of always just relying on guessing and hoping that we can guess the correct antiderivative, we're going to be learning more and more general techniques along these lines. The big one will go by the name substitution or the chain rule in reverse. And as we develop more and more of these antidifferentiation techniques in our toolbox, we'll be able to antidifferentiate a whole lot more functions without relying on just flashes of insight.